Okay, good afternoon. So let's start our lecture. So yesterday we talked about how to estimate the parameter of a population. So in particular, the population mean. All right. So we try to first of all get a point estimator to estimate mu, which supposed to be expectation of x, where all the individual in this population represent by x, and the behavior represent by the probability. Thank you. So still couldn't see, huh? Oh, laptop. Thank you. So, okay, so it's populations, and there may be infinite or finite individuals in these populations, and the behavior of this population or the measurements of these individuals, okay, we call it x, and this x follow a pattern distribution represented by f of x, and this x has an expectation equal to mu. So if you want to estimate this mu, so the first thing that we can do is to find a point estimator. So a point estimator, so this can be a point estimator, this can be a point estimator, this can be a point estimator, and this the maximum of all the x. This means that it is the maximum of x1 up to xn, where x1 up to xn represent the random sample. So these can be used as a point estimator for mu. But among all this, the best one is this one, while this obviously is not a very good estimator because it only used, or it's likely to be used to estimate the maximum of the population. But again, if the x are range from minus infinity to infinity, that means the x here, then this cannot be infinity. So it's not a very good way to estimate the maximum of the population. And in fact, it's also not good to estimate the center of the distribution, which is mu in some sense. All right, so usually we will use x bar. So x bar is the point estimator of mu. So it does not mean that x bar equal to mu. This is wrong. So what we are saying is that we take a sample, we calculate x bar. So that estimate from the sample can be used to estimate mu. Okay. So x bar is considered as an estimate for mu. All right. So with a head there makes a lot of difference. Mu by itself is a constant. Mu is a constant, represent the expectation of x. We may not know that. But mu hat is a statistics or a function of the random variable. So this case, I define mu hat equal to 1 over n summation xi, I from 1 to n. All right, so that is estimator. Okay, then so it's easy. We take a sample, look at the value of this sample, and then calculate x bar. So in that, after we obtain the sample, then we calculate the average of all the observations, x1 up to xn. All right? The difference, the notation that we used here, the capital letter represents a random variable. All right? While once you take a sample and you look at the outcomes of this sample, so you got the values. So they are represented by lowercase x1 up to xn. So x bar, the lowercase x bar, means that it's the average of all these observations. All right? So, so this is an estimate. Estimate. Well, this one is called an estimator. All right? Now, so it's not too difficult to see this. But then if we have so many estimators, all this can be used as estimator. So we may ask, which one should I use? Which one is a better one or the best among this set of estimators. So there's some criteria that we use. The one that we discussed here is, we call it unbiasedness, all right? Unbiasedness. What does it mean? It means that the expectation of your estimator is equal to the parameter that you want to estimate. So if you have this property, then we say that it's unbiased. And the bias is the difference between what the estimator you use and its expectation, the difference between these two quantities. What you expect from your estimator and what you want to estimate. That means mu is the answer, although I don't know what it is, but mu is the answer. So now I propose to use this mu x bar to estimate mu. So in the long run, then we expect this x bar, or the average of all the sample means, all right, we should be very close to mu or equal to mu, all right? So then it is unbiased. Otherwise, the difference between these two is called bias, all right? So an estimate is considered good if the expectation of it equal to what it's supposed to estimate. Then it's a good estimator, in the sense that it's unbiased, all right? So, but there another approach to the estimation is called interval estimator. So the idea is that, okay, we have an estimator, like for example this x bar. So we want to construct an interval. So usually for mu, the interval for the confidence interval for mu is something like this: x bar minus k times the standard error of x bar, and x bar plus k times standard error of x bar. So it's in this form. So the idea is that we try to construct an interval with this as a random variable, this as a random variable, such that the probability of this lower, the random variable, I call it theta L, okay, cover, okay, less than mu, all right? So mu between these two numbers, or two random variables with probability 1 minus alpha, all right? So that's what the idea of finding an interval that can be used to estimate the unknown parameter mu. All right? Okay, so you can see that the idea is that, okay, x bar is a point estimate for mu. So I start with x bar. I just subtract from x bar with this number, k, or with this random variable, k times the standard error of x bar. And the upper limit will be x bar plus k times standard error of x bar. All right? So now the question is, what are this k and standard error of x bar? So we start with the easiest one first. So if sigma is known, so if sigma is known, then the standard error of x bar is given by square root sigma square over n. All right? That means the square root of the variance. Square root of the variance of x bar, which is square root of sigma square over n, or you can write it as sigma over root n. All right? So then how about the k? All right? So now we are trying to work out the probability of x bar minus this k, sigma over root n. We work out this. So that the probability of this random interval cover the unknown parameter mu with probability 1 minus mu. So to find this probability, we have to rearrange it so that this is the same as all right? Then ask yourself, what is the distribution of this? The distribution. of this quantity. It's a random variable because x bar is a random variable. So we know that this x bar follow a standard normal with 0, 1 if the random sample is from a normal distribution with mean mu and sigma square. All right, so then it's quite straightforward. Then k is just equal to sigma alpha over 2. All right, z alpha over 2, which means that from a standard normal distribution, these are the 2 points minus z alpha over 2, such that the chance of this standard normal falls within here is 1 minus alpha. This area is 1 minus alpha. This part is alpha over 2, and this part is alpha over 2. So the chance the standard normal falls within this, between these two values is 1 minus alpha. So we find a random interval such that the chance cover this mu is equal to 1 minus alpha. So our confidence interval is defined as between these two random variables. So once you take a sample, then you calculate x bar, and sigma is known, n is known, so you substitute the formula, you get an interval. We call that a realization of that random interval. That means you really look at the data, and then now you get the numbers. Okay, so that is an interval. But this interval, okay, cover the true mean with, because it's a realization, so it's either it covers or it does not cover the unknown parameter mu. So we can only say that we have so much confidence. So now it's not a probability. Once you substitute the sample values in your formula in place of the random variable, then it's no more random. Just like if I toss a coin, I keep telling you the same story. Toss a coin, before you toss it, it's either head or tail. So the outcome is a random variable. But once you toss it and you look at the outcome, if a head, there is a head, it cannot be a tail. So the same applies here. Once you take the sample, you look at the values of this sample, then you already realize the random variable. So it's no more random. So in that case, we just have an interval based on this particular sample. All right. So we cannot say, oh, this interval covers the true mu with so much probability. No. It's just saying that the way that we do, or the formula that we have, is based on the random interval, which have, let's say, 95% chance. Let's say this is 95% chance that it will cover. So we interpret it as if we repeat to take many samples, and each sample we use this formula, this random interval, all right, to calculate. So that means I have many realization of these random intervals. And then out of so many realizations, 95% of them will cover the true mean. So in other words, maybe this is the true mean. I take one sample, calculate my confidence interval, another one, a third one, fourth one, and so on. Then out of so many of them, 95% will cover the true parameters. So that's what we interpret the coefficient, the confidence coefficients. All right? So now basically we try to construct an interval, a random interval, such that the chance of covering the mu is equal to 95%, or 1 minus alpha. So now the question is, okay, so what happens if the sample or the population does not follow normal distribution? That means the data or the population that we're looking at is not a normal distribution. Then what happens to our confidence interval? So, this is still true, but the question is, what is the distribution of this quantity? All right. If x1 up to xn, this random sample is not drawn from a normal population, what is the distribution of x bar minus mu over sigma over root n? So the answer is, okay, we don't know the distribution, but if your sample size is big enough, then your x bar minus mu over sigma over root n will be approximately follow a standard normal distribution. So in other words, I can still use the same random interval. X bar, that means this formula, all right? This random interval will cover the true mean with a probability approximately equal to 1 minus alpha. All right? So in other words, I can use the same formula, same confidence interval for sample taken from normal distribution, for sample which are not taken from a normal population, but the sample size is big. But also, we need to know sigma in order to use these formulas. If sigma is not known, you cannot use this formula. All right? So that's the case. Now, so we further, if we don't know sigma, then what to do? All right? So what to do? So now, so we want to estimate mu, but if sigma is unknown, all right, let's start with x1 up to xn. They are normal distributed. Mu and sigma square. All right? So these are things that we assume or we know. Then what is the confidence for mu? So naturally, we will look at x bar because this is the point estimate for mu. That means if you want to estimate the population mean, I take a sample and look at the sample mean. All right. The next thing is that, okay, I try to find statistics. Remember what's a statistic? Statistics is a function of the random sample, x1 up to xn. So can I use this one? No, because I don't know sigma. So this is not a statistics. That means I cannot use. So what can I do? I can replace this sigma by its estimate. That means I don't know sigma, but I'm going to look at my sample, try to get information about sigma from the sample. So the natural way to do it is to get the sample standard deviation. That means the square root of the sample variance. So I replace it. So now I consider this one. All right? So in order to find something that is related to this and in fact, what I want to do is to set something like this. And so that the probability of this equal to 1 minus alpha. So in order to do that, to find this k, in order to set up the formula, I need the k. So the k, in order to find the k, I need to know the distribution of x bar minus mu over s over root n. This quantity, I have to, in fact, this in statistics we call it pivotal quantities. So that is an expression involve mu. Mu is the parameter that we're interested in. And the rest can be obtained once we got the sample. So like x bar, once I got sample, I can calculate x bar. Once I got the sample, I can also calculate s. Once I got the sample, I know what n is. So basically, I can compute all this except that mu that I don't know. But this is exactly what I want, because now I'm going to find the distribution of this one, of this quantity, and then rearrange it so that I only have mu in one side of the inequality. So this follows a t distribution with n minus 1 degrees of freedom. So therefore, I choose this k from a t distribution, all right, alpha over 2 with parameter n minus 1. So this is t alpha over 2, n minus 1. All right? So then I rearrange it so that at the end, I will got this formula. X bar minus t alpha over 2, n minus 1, s over root n, and x bar plus t alpha over 2, n minus 1, s over root n. All right? So this is the random interval that I will use for my confidence interval. So once I take a sample, I calculate my x bar, calculate my s, substitute in the formula, I got an interval. All right. So we are quite confident that this interval will cover the true mean. All right. So that is provided that your data follow from a normal population. But then what happens if the data does not follow, this is not true? Then what to do? All right. Then So what can we do? If the sample size is big, we still can do something. So apply the central limit theorem, then we have this x bar plus x bar minus mu over, suppose this follow approximately normal. All right? But we don't know this one. So we are going to estimate it. So now the question is x bar minus mu s over root n. All right? So what is the distribution of this one? So this one, we can still treat it as approximately normal. All right. If your sample size is big, then the estimate of S to estimate sigma, that one should be quite close to sigma if your sample size is big. So we will treat this, all right, follow approximately normal. All right. So that's why we can replace this by a Z. All right. Alpha over 2, if your sample size is big. All right? So that is basically what we discussed. So sigma known, we have a we have a formula for that. And when sigma is not known, we have replaced by the estimate using the sample standard deviation to estimate it. All right? So basically the formula is always look like this. Plus or minus a constant times the standard error of x bar. So this one, if sigma is known, it will be this. If sigma is not known, it will be this. Then you are working on the k. Whether it is a z alpha over 2 or it's a t n minus 1 alpha over 2. All right, depends on whether the underlying distribution is normal or not, whether the sample size is big or not. All right. Okay, so today we continue with, okay. Okay, so today we continue with finding a confidence interval for mu1 minus mu2. So what we are going to do is like this. Okay, first of all, I want to get a point estimate for mu1 minus mu2. So naturally, I will look at x1 bar minus x2 bar. All right. So follow the same idea. So the confidence interval will be x1 bar minus x2 bar plus or minus a constant times the standard error of x1 bar minus x2 bar. So what is this? So if sigma 1 square and sigma 2 square, which are the population variance of the first population and the second population are known, then this is given by sigma 1 square over n1 plus sigma 2 square over n2, take the square root. And then what is this k? So we ask ourselves, so what is the distribution of this quantity? Because the expectation of this one is equal to this one. So basically it's the random variable x1 bar minus x2 bar, and then minus its expectation. That means it's in this form. W minus the expectation of W, then divide by the square root of the variance of W. So basically this is what we are looking at, this expression. All right? So what is the distribution? So the distribution, if the x1 up to x11 up to x1n1 are taken from a normal with mu1 and sigma 1 square, and x21, x22 up to x2n2 from normal mu2 sigma 2 square, that means x1, this is population 1 with mean mu1 and variance sigma 1 square, and population 2 with mean mu2 and variance sigma 2 square. I take a sample, so I have x1 1 up to x1n1 observations. This one, I take a sample, I have x21 up to x2n2 observations. So from here, I calculate x1 bar and s1 square. From here, I calculate x2 bar and s2 square. Of course, we know n1 and n2 as well. All right? But if sigma 1 square and sigma 2 square are known, then we don't need S1 square and S2 square. So this will follow a standard normal. A standard normal. So from that, we repeat the idea just mentioned for one sample case. We can give a confidence interval for mu1 minus mu2. All right? So what happens if they are not normally distributed? If all these x, if this is not true and this is not true, then what happens? So what we can say is that, okay, if your sample size is big enough, then we can still use this formula. All right. Why? Because we can still have this approximate normal distribution for x1 bar, approximate normal with mu1 and sigma 1 square over n1, if n1 is big. Similarly, x2 bar is normal mu2 and sigma 2 square over n2, where n2 is big. So therefore, the difference, again, will follow normal distribution with mean mu1 minus mu2 and sigma 1 square over n1, sigma 2 square over n2, minus, what is the term here? 2 times the covariance of x1 bar and x2 bar. But this one is equal to 0 because x1 bar and x2 bar are two independent random variables. So we can ignore it. All right? So, so if the sample size is small, then if we don't know whether it's from normal distribution or not, then we have problems. But if the underlying distribution, although it's not normal, but it's close to normal, then we can still use this formula to compute the confidence interval. More complicated is when sigma 1 square and sigma 2 square are unknown. All right? So, so this one divided into two scenarios. Maybe we don't know it, but we know that they are equal. Or we don't know, we cannot assume that they are equal. All right, this is in doubt. Okay, we don't know whether they're equal or not. That means we don't assume that the two variances are equal. All right? So, so we still have this one normal, mu1 sigma 1 square, and this one normal, mu2 sigma 2 square. Now the fact that if we know that the two variants are equal, all right, unknown, they're unknown, all right. Now if we don't have this piece of information that sigma 1 square equals sigma 2 square, then how are you going to estimate sigma 1 square? The variance from the first population. So naturally, you will just use S1 square to estimate sigma 1 square, right? So sigma 2 square, naturally, we will use the sample from the second sample from the second population and look at the sample variance to estimate sigma 2 square. All right? But now, if you are told that sigma 1 is equal to sigma 2 square, all right? If they're the same, let me call it sigma square, all right? So now, I asked you, now this sigma 1 square, I can use S1 square to estimate it. Sigma 2 square, I can use S2 square to estimate it. But now I tell you, the two sigma square are the same. Sigma 1 square and sigma 2 square are the same. So which one should you use? S1 square or S2 square? Which one to use? Which one to use? S1 square or S2 square? Or there's other choices? Of course, let me give you some more information, help you to decide. Suppose N1 is bigger than N2, then which one will you use? okay, let's say N1 equal to 100, N2 equal to 30. So which one will you use? S1 square or S2 square? Or some other ways? Or I don't know, right? Which one should we use? S1 square or S2 square? Can we combine the S1 square and S2 square? Huh? Okay. In fact, the idea is very simple, right? You have S1 square, estimate this one, S2 square, estimate. So one way is that I just take one of them. All right? Another way is to combine these two. Take the average, for example. All right? And of course, there's another way to do it. May I ask you, which one you believe is more accurate in the sense that the variation is smaller? So the variance, the S1 square, if from N1 is bigger, so we believe that S1 square should have a smaller variation or closer to its expectation. While S2 square with a smaller sample size, N2, it will be not so good as S1 square. All right? So if you take the average, first one we need to combine the two. Combine the two. Why? Because if you just look at S1 square to estimate sigma square, then you forget about the S2, the second sample, the information provided by the second sample. So you are not using every piece of information that you know to estimate sigma square. All right? So it's not good. Either use S1 square alone or S2 square alone. So we want to combine them. So a simple way to combine them is to take the average. But that's not good as well, because if S1 square comes from a bigger sample, I should put more weight to this estimate. So we should use a weighted average to look at it. So the weighted average to estimate this quantity is N1 minus 1 S1 square plus N2 minus 1 S2 square over N1 plus N2 minus 2. So this is a weighted average. Think of it, if N1 is big, then N1 minus 1 is bigger than N2 minus 1. So I put more weight to S1 square compared with S2. So this is used to estimate sigma square when sigma 1 square, sigma 2 square are unknown, but we know that they are equal. All right? So if this follow normal distribution, this follow normal distribution, then x1 bar minus x2 bar, mu1 minus mu2, all right? If they're equal, then this formula, right? This will follow a standard normal. Because sigma square over n1 is the variance of x1 bar, sigma square over n2 is the variance of x2 bar. So it just then divide by the square root of the variance of x1 bar, x2 bar, so it's a standard normal. All right? So now we don't know sigma, right? So we are going to estimate it by this quantity. This is the estimate for sigma. When sigma 1, sigma 2 are unknown, but they are equal. So estimate by this quantity. The weighted average of the two sample variance. Each of them can be used to estimate sigma 1 square and sigma 2 square respectively. And now we just combine them. So I replace this by, usually this is called SP square, all right? So we replace this by SP square. Then this is no more, all right, so it's like that. So this will become a T distribution, and the degrees of freedom is equal to N1 plus N2 minus 2. So that is the formula that we are going to use to construct the confidence interval for mu1 minus mu2, based on the idea of that this quantity follow a T distribution with N1 plus N2 minus 2 degrees of freedom. All right? So, what happens if this is not true? They are not from normal distribution, not approximately normal. Then what to do? How to estimate mu1 minus mu2? So we still used this formula, but because we don't have this part, then what can we do is to go back to this scenario. All right? If your sample size is big, although they are not normally distributed, I'm going to replace this by S1 square. I'm going to replace this by S2 square, and then treat it as approximately normal, standard normal. All right? But provided that you have a big samples, N1, N2 are big. All right, okay. So, so this is what we have. All right? So, yesterday we briefly talked about this one, right? Mu1 minus mu2. So, yes, so here, if sigmas are known, then you just apply the formula. Sigma 1, this is the formula. All right? So follow a standard norm. So I follow a standard normal, so this constant is standard normal. And then this is the standard error of x1 bar minus x2 bar when sigma 1 square and sigma 2 square are known. So if not known, but the sample size is big, then yeah, unknown variances, but large sample. We have large samples, then we just replace the sigma 1 square and sigma 2 square by their corresponding estimate. And this is an approximate distribution. All right? Okay. So then how about unknown but equal variance? So here I don't specify that the sample size are big. All right? I have small sample size and the distribution of the population is normal, and also on top we have equal variance. So in this case, so this will follow a standard normal. So this quantity will follow standard normal. So just now I tried to convince you that this sigma square can be estimated by S1 square, can be estimated by S2 square. So I have to combine them in the sense that I put a weighted average. Weight this one by the sample size minus 1, and this one by sample size of the second sample. And then combine these two together is N1 plus N2 minus 2. So that one is used to estimate sigma square. So once you replace the sigma square by its estimate, so this one is not normal, but instead of a T distribution with these degrees of freedom. All right, so this is the formula. So here I just make it more clear mathematically. This follow a chi-square. This follow a chi-square. All right? And two independent chi-square add together. All right? Add together. So follow a chi-square. You recall, if W1 follow chi-square with degrees of freedom M1 and W2 chi-square with M2, and if they are independent, then the sum of them will follow again a chi-square, and the parameter is just the sum of the 2 degrees of freedom. So it is N1 plus N2 minus 2. So now another properties that we mentioned in chapter 5 is that a standard normal divided by the square root of a chi-square distribution divided by the corresponding degrees of freedom, that will follow a T distribution. This is standard normal, and this is chi-square with k degrees of freedom. All right. So all this is just the theory behind, or the mathematics behind, to show that once you replace the sigma square by its estimate, all right, by the estimate, then it follows a T distribution. Okay, so that's the results. That's the results. So it follows a T distribution. All right. So based on that, so this is the T distribution, the lower limit, and the upper limit for alpha over 2. All right? Rearrange it, so we got this look very complicated formula, but the idea is that we want to estimate this one. This is the point estimate, this is the constant, and this is the standard error, or estimate of the standard error for x1 bar minus x2 bar. All right? So if you have big samples, all right, then in that case, this t can be replaced by a standard normal, because the t distribution with n degrees of freedoms approach to a standard normal if n gets bigger. All right, if this is true, all right, then the t distribution behaves like a standard normal when your degrees of freedom is getting bigger. You can check easily that, for example, n equal to 30, then like for example, this t 30.025 is quite similar to 0.025. Of course, not exactly the same, but not too far away from that point. All right, so remember, if your sample size is big, you can replace the t, the constant related to t distribution, replace it by standard normal. So here is an example. So I have two groups, all right, students using different teaching methods, 12 students and 10 students respectively. So these are the sample size, N1 and N2. All right? And at the end of the semester, we ask the students to take the same exam. And then this is X1 bar, this is S1, all right? And this is N2, X2 bar, and S2. So we want to construct a 95% confidence interval. So we just substitute the formula, because now we have two samples, one from population 1, the other from population 2. So, and we assume that the population is approximately normal. All right? And not only that, we also assume equal variances. All right? So we apply the formula, get the pooled, this is called pooled variance, as pooled variance. All right. So in other words, if you believe that these two populations with the same variance, so the sample that you've taken from the first population and the sample you've taken from the second population, you can combine these two samples using this formula, all right? N1 minus S, S1 square plus N2 minus 1, S2 square over N1 plus N2 minus. Using this formula to get a pooled variance. That means it looks as if you put these two samples data together and get an estimate for the variance. All right? So we substitute all this in the formula, and also we calculate this. This is N1, which is 10 plus 12 minus 2, so it's 20. All right? So this is the confidence interval. The difference between mu1 and mu2 is between 0.69 and 7.3. If you notice that the confidence interval for this particular two samples, all right, does not cover 0. So in other words, these two samples data shows that maybe mu1 minus mu2 is different from 0. Because it does not cover 0, that means we believe, we're quite confident that mu1 minus mu2 does not equal to 0. And in fact, mu1 seems to be bigger than mu2. All right? Okay, so now what happens if we look at the difference between two means, all right, for paired data, All right? So in other words, we are looking at the dependent data. So we obtained, for example, in this case, we run a test for a new diet of 15 individuals. So N is 15, and then each individual we have two observations. One is the weight before the completion of the test, And the other one is after, okay, a test on the new diet, all right? So that means they run a course. One is with new diet, all right? And then each individual will take the weight before they participate in this program, and then after that, we also look at its weight. So basically, X1, XI, YI, all right, this is before weight, this is after weight. So these two, XI and YI, they are from the same individual, So they are not independent, they are from the same individual. So we consider they are dependent data, or sometimes refer as the paired data. All right? So they are from the same individual and are related. So we want to determine the effectiveness of this diet. So we would like to look at the difference. Look at XI minus YI. Of course, you can also look at YI minus XI. You can look at this as well. All right? It doesn't matter, so long as it's the difference between the two. So usually it is maybe after minus the before weight, then it's YI minus XI. Or you can just have XI minus YI. All right? But you have to get the right interpretation. So when you look at this DI, so DI, all right, DI, if it's positive, it means that the before weight is bigger than the after weight. If DI is negative, then that means after joining the program, at the end, the weight is heavier than the before, if you define your DI as XI minus YI. So what I'm trying to say is that the behavior of DI, for example, DI bigger than 0, then if you define it like that, then it means XI is bigger than YI. On the other hand, if you get DI negative, that means your XI is less than YI. All right? The before weight is less than the after weight. All right? But if you define it like that, then if you define your DI like that, then DI bigger than 0 means that YI is bigger than XI. So the after weight is bigger than the before weight. All right. So it's very simple now. It basically, instead of looking at XI and YI together, we just look at the difference. We don't care about what the absolute, what the values of XI and YI. I just want to know the difference between XI and YI. So I call it DI. So I just need the information about all these differences. And suppose this one is considered taken as a population. So each population is an order pair, X and Y. All right? I take X1, Y1 for the first individual taken from this one. X2, Y2 is the second individual taken from the population. So all this value. But instead of looking at XI, YI, I just look at D1, D2, and so on. So Xn, Yn, I look at Xdn, where DI is defined as XI minus YI. All right. So I can consider that for each individual, although I can measure their before and after weight, but I can treat it as just D. So in other words, I have individuals in this population, each one I got the D, which is the difference between XI and YI. And I assume that this D follow a normal distribution with mean mu D and variance sigma D squared. So this go back to one population case. It's one population case. So you ask yourself whether you know this sigma D squared. Usually we don't know that. So we assume that we don't know. Then how to estimate mu D? All right? Mu D. So the way that we do it is to take the average of all the D's, and then the point estimate for the variance of D is given by SD squared. So in other words, you just replace the XI, YI by DI, which is the difference. Then you just look at your sample, you just concentrate on DIs, D1 up to Dn. So you get the average, which is D bar, you get the standard get the variance, the sample variance, which is each di minus d bar, square it and sum them up, and then divide by n minus 1. So the confidence interval will be the average minus its average, the expectation, divided by the standard error, which is SD over n. So this follows a t distribution with n minus 1 degrees of freedom. It's nothing, it just replace the d's, we replace all the individual instead of xi, yi, and replace by di. So it's just like one population, one sample case. So this is exactly what we did in the one sample case. So the confidence interval is given by d bar, which is a point estimate for this quantity, a constant times the standard error of d bar. And this constant is taken from a t distribution with n minus 1 degrees of freedom. All right? So when sample size is big, so what does it mean? It means that now I can assume that this d bar minus mu d over s over root n, or sd over root n, this is supposed to follow a t distribution. But now with n big, then I can consider this approximately follow a standard normal, 0, 1. All right? So now I can replace this quantity, this t, by z. So instead of t alpha over 2 n minus 1, so now I replace by a standard normal, a critical value taken from a standard normal distribution. All right? So let's look at this example. We have 20 students, so n equal 20. Oh, sorry. Okay, we divide it into 10 pairs. All right, 10 pairs. All right? So each member of the pair are having approximately the same IQ. By the way, so sometimes we will try to construct the pairs xi and yi, all right, such that these two observations come from the two different individuals, but they are considered as almost the same in all aspects, except the quantity, except the value that we are looking at. All right. So in this case, we assume that the pairs, we have 10 pairs, so their IQs are approximately the same. So I'm going to do something that, okay, may be affected by the IQ. So now in the pair, these two persons in the same pair, they are considered as they are equally with an equal IQ. All right. So one of them will be selected at random and assigned to a mathematics section using programmed material, while the others is the others as unfortunate ones assigned to sit for the lecture. All right, just like what you have here. All right. So basically, we are looking at the results of going for a structured or programmed material, using a programmed materials. All right, this one way of teaching. The other one is going for lectures, physical lectures. All right, so we can think of this as webcast. Right, this one is the really physical lecture. So we want to compare these two teaching methods. One way to do it is to select students. All right, assign a group of students to under this programmed materials methods. The other one is under the lectures method. All right. So that one is two independent samples. All right. But there's this problem that we try to look into it, because what happens if those bright students, all right, assigned to, right, the professor lectured group, all right. So at the end, this group has a better exam results, but it does not mean the professor taught well, right? It just happens that they have good students in that group. So we try to eliminate this impact about different abilities. So what we're going to do is to find two students, form a pair, and they're supposed to be equally, they are equally good in the IQ or academic ability. So one assigned to the material program, the other one assigned to the lecture group. All right? Then we look at at the end, we look at their exam score. So the difference may be due to different teaching methods because they're of same academic ability, so we believe that if there's difference, the difference may be due to different teaching methods. So that's the idea we use this paired data. So we try to form a pair, and this pair, each one in the pair, suppose they're equally good academically, so same IQ. All right? So at the end of the semester, each group was given the same exam and the following results were recorded. Yeah, maybe I should record down who attend the lecture. All right? And then at the end, I go and look at, whether, but this is not a pair because I did not pair. So I just have a small group that attend lectures. A big group, maybe that big group also can divide into watch webcasts regularly or watch the webcast sparsely, maybe at the end or last few days or before the exam, then they watch. All right. So see how the exam score look like. But this example, we really look at pair, so it eliminate the impact or the effect due to different academic abilities. All right. So this is the result. So first pair, I'll go through the materials, the programmed materials. Wow, 76. Wow, those go for lectures 81. All right. So this is the results, the difference. There's some positive, some negative. Look at the positive. 1, 2, 3, 4. 4 out of 10 are positive. Positive in this, okay, this one is xi, yi. So xi, this is xi minus yi. All right? So, all right? So there are only 4 positive and 6 negative. So can I conclude that the programmed material, the program materials, teaching method is inferior because there are only 4 positive. That means out of 10 pairs, 4 have this positive. That means 4 pairs give the results that this program is better than the lecture program. While 6 out of 10 is the other way around. But this is not what we want to test. All right? What we want to test is that this D, mu D equals 0 or not. This is what we want to estimate. So we want to find a 98% confidence interval for the true difference in the 2 learning procedures. All right? So from the data, we work out the average is minus 1.6. And the standard deviation is 40.7, sorry, the sample variance is 40.71. So we base on the formula with 10 pairs. Now you have to pay attention. Now, although there are 20 individuals in this example, but we are going to group them in pairs. Within the pairs, they are linked in the sense that they have the same academic abilities. All right, so the results is look at their exam marks and see which one has better. So we look at the difference between these 2 individuals in the pair, in the same pair. All right, look at the difference. So altogether, there are only 10 difference. So the degrees of freedom is 10 minus 1, not 20 minus 1. It's 10 minus 1 because we have only 10 differences. And we are looking at the difference instead of individual x and y. We are looking at D, which is x minus y or y minus x. All right, so this is how we apply the formula, and then we get, so the confidence interval that we construct based on this 10 pairs of observations is minus 7.3 to 4.1. So what does that mean? It means that based on these 10 pairs, we find out that the difference, the expect difference, is likely covered by this interval minus 7.3 to 4.1, which covers 0. So in other words, this sample data illustrate that mu d can be 0. All right, can be 0. All right, so that's how we look at it. So now we talk about three types of confidence interval. Confidence for three types of problems concerning about mu, about the population. One is one population, mu. The other one is mu1 minus mu2. The third one is a special case, mu d, which is the difference between two observations from the same individual, or if they're not from the same individual, from the same pair, and this pair are paired in such a way that they are similar in all aspects except the one that we are looking at. All right? Okay, so next we move on to talk about another important quantity, is the variance. All right? So we want to find the confidence interval for the variance, sigma square, or if we have two populations, we are not looking at this. This is hard. So we are looking at the ratio. We are looking at the ratio. All right? So, in fact, our most concern is whether sigma 1 equals sigma 2. If you try to find the confidence for sigma 1 square minus sigma 2 square, it's the same as whether we want to check whether sigma 1 square minus sigma 2 square equals 0. But it's the same effect if I find out whether this equal to 1 or not. If the ratio equal to 1, that means sigma 1 square equals sigma 2 square. So we look at, if I want to check whether sigma 1 square equals sigma 2 square, there are two ways to do it. One is to look at the difference. So if the difference equals 0, that means they're equal. Second way is to look at the ratio of the two. If the ratio equal to 1, that means they're equal. All right? So we want to find the confidence for sigma square and find the confidence interval for sigma 1 square over sigma 2 square. Okay, so first of all, so assume that the data is from normal population. So x1 up to xn is a random sample taken from a population. Either is normal or approximately normal. All right? With mean, mu, and variance sigma square. So we are interested to find a confidence interval for sigma square. The first thing to do is to find a point estimate. Point estimator for sigma square. So naturally, we'll look at the sample variance. Sample variance to estimate sigma square. So that is our starting point. All right? Okay, so we look at the sample variance. But in fact, okay, so this is a point estimate for sigma square. Now, so next we want to find a confidence interval. So as usual, because if the population follow normal mu sigma square, so this is what we are interested. So we are looking at this mu. So there are two possibilities, whether this is known or whether this is unknown. All right? So first of all, we look at mu is known. Now when mu is known, so we use a slightly different approach. We asked ourselves, what is xi minus mu over sigma. Xi minus mu sigma square. Xi minus mu over sigma. This is a standard normal. I choose this quantity. Why? Because mu is known. Sigma is the only thing that I don't know. And in fact, this I don't know thing, quantity, is the one that I'm interested to find the estimate. Xi, once I got the sample, I look at the sample data, I know what xi is. All right? So then I look at xi minus mu square. So this one is a chi-square distribution with 1 degree of freedom. And when I sum them up, it is chi-square n. Okay? So I look at, first of all, I want to estimate sigma square. So I want to derive the formula, or at least give you some idea how the formula, how we get the formula. So I'm interested in estimate sigma square. So I look at a point estimator, which naturally is the sample variance, S square. Next, all right, I want to get the confidence interval. All right, so I divide the unknown parameter mu into two parts. One is known. Now once it's known, then naturally I will make use of this information. So I start with xi minus mu over sigma. Why I choose that? Because this xi minus mu over sigma, all right, mu is known, so it's a constant. Xi, I can get it from the sample. And sigma, unknown, we don't know. But this is exactly what I want to find something about it. All right, so I'm interested in this one, so it's a standard normal. All right, next, I try to square it, so it becomes chi-square. Now, why I have to do that? Okay, because basically it has something to do with this sample variance. I want to draw similar thing like a sample variance, except that I don't need to, you see, this used to estimate sigma square in this form. So I try to construct something similar to this one, except that now I have more information. I know what mu is. So instead of using x bar, I replace it by mu. Why I have to do that? All right? Sample variance is inferior compared with this quantity. Why I say that? Because once you know fixed mu, you know mu is a constant, while x bar is a random variable. So you try to, mu is there. If you use this mu, I know how it behaves. Now I don't know mu, I just use x bar to estimate it. So in other words, you just guess. So when you guess, that's not so accurate, right? So therefore, the sample variance is not very good to estimate sigma square if you know there's something maybe slightly better to estimate it. That's why if you know the mu, I don't need to estimate mu, I just use mu. So that's why I look at this one. This is chi-square n. So now, naturally, follow the same idea. All right? This is what I just mentioned. So this is chi-square n. And then now, I write down. This is chi-square distribution with n degrees of freedom. I look at these 2 points. This is the point here, and this is the point here. And this is the random variable which follow chi-square with n degrees of freedom. So this random variable between these two numbers with probability 1 minus alpha. So I rearrange it with sigma square in the middle. So I multiply this to the other side, divide this out, so I got this part. So this inequality becomes this one. When after I rearrange it, this inequality, when I rearrange it with just sigma square on one side of the inequality, it becomes this inequality. So now I come up with a random interval that will cover the unknown sigma square, all right, with a probability 1 minus alpha. So once I have the data, I use this formula to compute my confidence interval. This is provided that you know what mu is. But this is most likely is for mathematical interest, because in real life, you don't know mu, all right? There's seldom a problem that you know mu, but you don't know sigma square. All right, but this is for mathematical interest. This is the formula when mu is known. So we use this formula, all right? Then how about with mu unknown? Then in that case, I cannot use this formula because now mu is unknown, so I cannot use this formula. So I have to replace it by x bar. In that case, this one follow a chi-square distribution with n minus 1 degrees of freedom. Because s squared is equal to 1 minus, or n minus 1 s squared is summation xi minus x bar squared, I from 1 to n. All right? So this quantity is good because once you got a sample, you can have this xi, you can have all the x bar, you can have all the xi and x bar, and the only thing that you don't know is sigma square. So I have this quantity which involves sigma square, and then the rest of this expression will be known once I got the sample. All right? So, and I also know the distribution is chi-square n minus 1. So I substitute. So this quantity follow a chi-square. This time is chi-square n minus 1 degrees of freedom. Look at this and this. So this quantity falls within these two numbers will have a probability equal to 1 minus alpha. This is 1 minus alpha. Rearrange it with the sigma square, the inequality with sigma square on one side of the inequality. So this part come from this inequality. And this inequality comes from this inequality. So now I have sigma square in the middle, and the two ends of the two inequalities are random variables. So this is the formula. All right. So I just tell you how all these intervals are obtained. All right. You can just use the formula. So I tried my best to explain the rationale behind how to derive all this formula. So you have to be aware of what the underlying distribution are and what are the assumptions that we make. Here we assume that the populations are normally distributed. Otherwise, these are not true. Summation xi minus mu square over sigma square. This one follow a chi-square distribution with n degrees of freedom, provided that your sample are from a normal with mean mu and variance sigma square. All right, this is the assumption that we make. The data or the sample are taken from a population which follow a normal distribution with mean mu and variance sigma square. All right? Okay. So that is the confidence for sigma square. So if you so now if you have this, let's say it's W between sigma square and WU and WL and WU. All right? Okay, what I mean is that if we have an expression or two random variables or this random interval cover sigma square with probability 1 minus alpha, then if I take square root of all this, so what is the probability? Are these the same as this one? Same event? It's the same. You just take the square root. Okay. In other words, this inequality, all right? If you take a square root, if this is true, is this true? Of course, provided that they are positive, and all these are positive. So take the square root of sigma square. So this is sigma. So, square root sigma square. So these two are equivalent events. So therefore the probability is 1 minus alpha. So the confidence interval for sigma is just take the square root. Take the square root. All right? By the way, please take note. This is the confidence interval, right? What is this number? All right. This number, okay, my notation used here is that this is the number on this side, so that the chance bigger than it is 1 minus alpha over 2. So that's what it means. So when you apply this formula, make sure that you get the right critical values. Well, this number in my notation, unfortunately, notation may not be universal. This means a point here, such that the probability bigger than this point is alpha over 2. All right? So that's what it means. But you will check easily. You divide by a bigger number, so this number is smaller, because the numerator are the same. Okay, so divide by a bigger number. So this number is supposed to be small, and this one is divided by a smaller number, so this one is supposed to be big. All right, so just double check, make sure that you get the right quantity. All right, okay. So naturally, the next question. This is an example. So we have 10 observations. This is the volume. All right, for 10 cans of bleach. All right. So these are the 10 numbers, and we want to construct a confidence interval for the variance of all these cans. All right. So the infinite number of cans of peaches, we just take a sample of size 10. All right. And these are the volume. All right, of these peaches. So we want to estimate sigma square. All right. So we assume normal distribution. The volume follow normal distribution. So here we calculate the sample variance, and we also took the two values for a chi-square with 9 degrees of freedom. Then this point, 2.7, is a point where the probability less than it is 0.025. Greater than it is 0.975. The other number, 19.023, greater than this is 0.025. All right, this probability is 0.025. So we have these two numbers. Then we substitute the sample data. So it's 9 times S square. So sigma square is between 0.135 and 0.954. So that is the variance, that confidence interval for the variance. So the variance, we believe that it is somewhere covered by this interval 0.137 and 0.954. All right. Now how about the ratio of the two variances? And here we try to look at the problem without knowledge of the means. So what we can do, so this is an important assumption. So this is a random sample from a normal population or approximate normal. Similarly, the second sample also taken from a normal distribution with approximately normal. All right? So we assume that we don't know mu1 and mu2, and we are interested in getting the ratio, getting a confidence interval for this ratio. All right? So we repeat what we did just now. So we don't know mu1, so we use this. So this follow n minus chi-square n 1 minus 1. If mu1 and mu2 are known, which may not be practical, but then you just have to modify it. So instead of looking at summation, the numerator here is summation xi minus x bar square, the numerator. So if these are known, you just replace this by mu1, and then the degrees of freedom now becomes n1. So that is how you do it. Although I did not discuss here, but you have to know the idea. So if mu1, mu2 are given, then I cannot use this formula. Why? Because this is not a very good formula. Because you know mu1, mu2, you have to use this information. And if you don't use it, you just estimate mu1, mu2 by x1 bar and x2 bar, which is inferior in some sense. So in that case, we have to consider instead of summation xi minus x bar, you consider summation xi minus mu1 square. All right, and then over sigma square. So this one follow a chi-square with n1 degrees of freedom. All right, but since most of the cases we don't know mu1, mu2, so we start with mu1, mu2 unknown to us. So this follow a chi-square distribution with n1 minus 1. This follow a chi-square with n2 minus 2. And then we take the ratio. This is a chi-square distribution. This is a chi-square distribution divided by its degrees of freedom. Another chi-square distribution divided by its degrees of freedom. Take the ratio of this one. This one we call it F distribution. And the parameters are n1 minus 1 and n2 minus 1. So this cancel out, this cancel out. So this is the expression. All right. This expression is good. What? Because it involves sigma 1 square over sigma 2 square. And once we get the sample, the two samples, we can calculate S1 square and S2 square. And we also know what N1 and N2s are. So therefore, we just have this F, this follow F distribution. So between these two numbers. So this is the F distribution with degrees of freedom N1 minus 1 and N2 minus 1. And then now, this number is this one, such that bigger than this number with probability 1 minus alpha over 2. That means this is 1 minus alpha over 2, while this is alpha over 2. All right? And this value, referring to this point, such that greater than this value with probability alpha over 2. That means this is alpha over 2. F is not symmetrical. Huh? So it's like that. So now I rearrange this. This in fact means, this means that S1 square over S2 square times sigma 2 square over sigma 1 square. It's like that. All right? So I rearrange it so that with sigma 1 square over sigma 2 square in the middle, then I have this formula. These are the random interval. So this is my confidence interval. All right? So this is the formula. So remember, this is the value, all right, for which it is the probability. This is the value for which greater than it is alpha over 2 for f n1 minus 1 and n2 minus 1 degrees of freedom. This, all right, I'm sorry, I make a mistake. So this is, I reverse the order, all right? So it's n2 minus 1 and n1 minus 1, all right? So, in fact, the correct expression should be, this one in fact is 1 over n f n1 minus 1, n2 minus 1, 1 minus alpha over 2. But these two are the same, all right? That is, a point which is greater than this with probability 1 minus alpha over 2, when you take the reciprocal, is the same as a point that is greater than this point with probability alpha over 2, but from a different distribution. We swap the 2 degrees of freedom. Why? It's the same thing. So when you look at V over N1 or over K1 and W over K2, all right? So when you look at these two numbers, between these two numbers, when you take the reciprocal, it becomes W over K2, V over K1, then this is 1 over B and 1 over A. Is this correct? No. Once you take the reciprocal, you have to reverse the inequality, right? 3 is bigger than 2. So 1 over 3 is not, compared with 1 over 2, it's less. So you have to reverse the inequality. So I just take the reciprocal, change the numerator and denominator. So I got this one. So this one, change the numerator and denominator, or swap the numerator, it becomes 1 over A. A becomes 1 over A, B becomes 1 over B, and also reverse the inequality. So by doing so, you can show that this quantity is the same as this quantity. All right? All right. How you use the formula. All right? So this is just what I said. We try to work out the critical values. You have to take the reciprocal. That means you swap the numerator and denominator. All right? Okay. So, all right. So, you just have to remember this fact. In other words, F, let's say 510 with 0.975, for example. This is equal to 1 over F 10 5 and 0.025. 0.025. All right. So in other words, this is the point for F510, all right, such that this is the point, such that the probability here is 0.975. It's the same as the point from F10 5, all right, and then you look at this point. This point, it is the denominator, all right, such that the probability greater than this point is 0.025. But I'm not saying this point is the same as this point, but it's the 1 over the reciprocal of this point is equal to this point. So these two points are not the same, but just the reciprocal of one another. All right? So, so same apply before. So if you are interested in the sigma 1 over sigma 2, then you just take the square root of the two end point, or the upper and lower limit of the confidence interval for sigma 1 square over sigma 2 square. All right? Okay, so here's the example. So we have two, again, we have two placement tests. So for two groups, 25 boys and 16 girls. So the boys have an average grade 82 with standard deviation 8, and the girls have standard 8 with standard deviation 7. So this is S1 square, also S1, and this is S2. All right? And find the confidence interval. So we assume that the data are from normal distribution, all right? And yeah, we assume that the data are from normal distribution. So we want to look at the ratio. So we apply the formula with N1 25, S1 8, N2 16, S2 is 7, and 98% means alpha equal to 0.02. So these two, if you have a calculator, you have computer, you can work out this easily. But if not, if you are only provide a statistical table, then here I try to look at these two quantities, which are the this point, because we don't have 24, 15. You just take the nearest two and then take the average. All right? And this is another way to do it. All right? It takes a linear interpolation. So don't worry about this linear interpolation. So I will accept you take the nearest. Okay, if you couldn't find it in your F table, take the nearest possible degrees of freedom. Or no, then you take the two. For example, 15 is not there. You look at F24, 12, and F24. I don't know whether it's 24. I forgot the table that I gave you. All right. So I take the average of these two. So as an for this one. Oh, sorry, 0.01. All right, 0.01. All right. So once you have these two critical values, then you can calculate the confidence interval. For sigma 1 over sigma 2 is 0.95, 0.395, and 3.84. And you notice that this confidence interval covers 1, which means that from these two data, it seems that sigma 1 square equals sigma 2 square. All right? While if you take square root, the confidence between the ratio sigma 1 over sigma 2 is 0.628 and 1.96. All right? Okay. So I think, sorry, I don't have time to, you try to figure out using an approximate value to get these two from the F table that I gave you in the IVOE or Luminous. Look at it, how to do it. All right. So So we accept the reasonable approximation. So either you take the nearest one or take the average between the two, all right? Or even better, take a linear interpolation. Okay, so I think I finished chapter 6. So next week we continue with chapter 7. This is on hypothesis testing. All right, that's a very common technique used. And the p-value, I think you heard about it, so we'll discuss all this about p-value thing. All right. Okay, so we stop here.